Hey everyone, I'm Dr. Chem, and welcome to another explainer. So I want you to think about this for a second. Can one simple mathematical rule actually govern the totally chaotic, invisible flow of electricity? Whether we're talking about the wiring hidden in your walls at home, the microscopic circuits packed into your smartphone, or even those massive industrial power grids, they all completely rely on the relationship between three fundamental concepts. We've got voltage, which is the electrical push. We've got current, the actual flow of electrons, and resistance, which is basically the obstacle fighting against that flow. Today, we aren't just going to sit around and theorize about these concepts. We're actually going on a practical, hands-on journey. Our objective? We are going to verify that the current flowing through a conductor is directly proportional to the applied voltage, as long as the physical conditions stay constant. It's going to be fun.
Okay, so here is the roadmap for our scientific process today. We'll start with the fundamentals of Ohm's law, move into the experimental apparatus, go through a step-by-step verification, analyze the graph, talk about precision and errors, and finally wrap up with the limits, specifically non-ohmic behaviors.
Let's kick things off with Section 1, the fundamentals of Ohm's law. Way back in the 19th century, a brilliant German physicist named George Simon Ohm was investigating how electricity behaved. And from his incredibly tedious experiments came this beautiful, elegantly simple equation, V equals I times R. Now, if you do anything with electronics, you already know this is literally the absolute bedrock of circuit analysis. Put simply, voltage, that's our V, is the pressure pushing the charge. Current, the I, is the actual flow of those electrons moving along. And resistance, the R, well, that's the obstacle course fighting that flow. Ohm's law basically says that if temperature and other physical conditions stay constant, the current flowing through a conductor is directly proportional to the applied voltage. Basically, push harder and more flows.
All right, moving right along to Section 2, the experimental apparatus.
To actually prove this in reality, we need a complete testing environment. It starts with our DC power supply, like a battery, which provides that essential electrical push. Following the path of the circuit, we have a plug key to safely open and close things up, and an adjustable rheostat, which acts kind of like a valve to control the flow. And right in the middle of it all sits our unknown resistor, labeled R. That's the component whose properties we're actually trying to test today. Now, here is where you really need to pay attention, because to measure what's happening, we have to follow some strict connection rules. This is absolutely crucial for electrical safety. We use an ammeter to measure the current, right? Well, it absolutely must be connected in series, meaning it sits in the direct line of the flow. Why? Because it literally needs to count the electrons passing through it. The voltmeter, on the other hand, measures the potential difference across the resistor. So it has to be connected in parallel, basically hugging the component from the outside. If you mix these two up, the very low resistance ammeter will cause a massive short circuit, and you definitely don't want that.
Okay, Section 3, step-by-step verification.
So, how do we actually run this experiment? The crucial point here is that by systematically changing the voltage using that rheostat, we can just sit back and watch how the current responds. First, we start with the power supply down at its minimum. We slowly adjust the rheostat to allow just a specific small current to flow. Then, we freeze. We write down exactly what the voltmeter and the ammeter say. After that, we tweak the rheostat to bump up the voltage a little bit more and record again. We just repeat this cycle until we have a really solid set of 5 or 6 readings. But, and this is important, you have to be super careful not to leave the power on for too long. If you do, the resistor will heat up, and remember that constant temperature condition we mentioned? Yeah, that would completely ruin it.
Up next, Section 4, analyzing the voltage-current graph.
Let's look at some actual lab data. Here, we're using a nominal 1 kilo-ohm resistor. In our first observation, we measured 2.03 volts, and the ammeter gave us 2.1 milliamps. If you do the math, divide the voltage by the current to find the resistance, you get roughly 1 kilo-ohm. Makes sense, right? But check out observation 2. We basically doubled the voltage to 4.02 volts, and look at the current. It responded proportionally, jumping right up to 4.1 milliamps. The ratio between them remains completely constant. And here is where it gets really satisfying. When we plot all of those data points on a graph with voltage on the y-axis and current on the x-axis, we do not get some random, messy scatter of dots. No, we get a perfectly straight line passing right through the origin. The simple fact that it's a straight line is visual confirmation of that direct proportionality Ohm proposed. And it gets even better. If you calculate the slope of this line by dividing the rise by the run, that slope gives you the exact measured value of the resistance. It's just a beautiful mathematical proof.
All right, Section 5, Precision and Minimizing Errors.
Now, we all know real-world experiments are rarely as perfect as a textbook. Let's say you try to measure a really tiny resistance, like a strain gauge used to measure stress on a bridge. Your standard, everyday handheld multimeter is honestly going to lie to you. In a standard 2-wire setup, the wires connecting the meter to the resistor have their own slight resistance. So when the meter pushes a test current through, some voltage actually drops across the leads themselves, and that adds a huge percentage of error to your reading. The fix for this is the 4-wire, or Kelvin method. By using a separate, high-impedance circuit dedicated solely to measuring the voltage right at the component's legs, we can completely eliminate the error introduced by those test leads. It's incredibly clever. And we can take this precision even further with a tool called the Wheatstone bridge. This is a diamond-shaped circuit that lets us measure unknown resistances with extreme accuracy. Here's how it works. You adjust a known variable resistor until the highly sensitive galvanometer right in the center reads absolutely zero current. When it hits zero, we call that being balanced, and it means the ratios of the resistors on both sides are perfectly equal. Because it relies on this null reading of zero, it is incredibly insensitive to annoying fluctuations in your power supply.
Finally, Section 6, Limits and Non-Ohmic Behaviors.
Okay, it's time for the plot twist. Ohm's law is called a law, sure, but it's not actually an unbreakable rule of the universe like gravity. It absolutely fails under some very common conditions. We call materials that follow the rules ohmic materials. A standard carbon resistor? That's ohmic. It gives you that beautiful straight line on the graph. But what if we swap that out for a standard light bulb with a tungsten filament? If you run the exact same experiment, the graph curves wildly. Why? Because tungsten is non-ohmic. As current flows, that filament has to get incredibly hot to produce light. And that intense heat fundamentally changes the physical properties of the metal, causing its resistance to just skyrocket as the voltage increases. So what's actually happening at the microscopic level when this breaks down? Well, at high current densities, the electrons traveling through the wires start violently colliding with the atomic lattice of the material itself. This generates localized vibrations, essentially heat waves, which we call phonons. We know this as Joule heating. Those phonons act like a really chaotic, dense crowd that the electrons have to fight their way through, and that physically increases the material's resistivity. And if we zoom in even further, down to nanomaterials and tunnel junctions, we see effects like inelastic tunneling, where conductivity changes depending on the bias you apply. Ohm's simple linear equation, as great as it is, just cannot account for that level of quantum and thermal chaos. Which leaves us with this final pretty fascinating thought. Managing all that current-generated heat isn't just a headache for the people designing microchips. It's the exact reason we have strict electrical safety ratings on household wiring and industrial circuits to prevent catastrophic failures. Through this experiment today, we've seen just how crucial it is to verify these principles, watching out for pesky errors like test lead resistance, port connections, and taking precautions to maintain constant temperatures. Because ultimately, deeply understanding this fundamental relationship between voltage, current, and resistance is exactly what allows us to build the modern world safely. I am Dr. Chem, and I really hope this explainer empowered you to see the structured, mathematical laws hidden right beneath the spark of electricity. I'd love to invite you to explore more practical science and engineering experiments right here on the channel. Keep questioning, and I'll see you next time.